and some new observation sequence comes in, I could have told you which one was most likely using just the forward recursive algorithm, right? It requires the A's and the B's, but that's what it means to have trained up the HMM. So I want to tell you about the rest of the problems, but I'm just going to tell it to you in words. I'm not going to give you the math. And you can go look. There are a bunch of tutorials on HMMs out there if you want to do the math. They're pretty straightforward, all right? So the forward recursive algorithm that I just showed you can compute the likelihood of being in state I at time t and having seen all the observations up to time t, given that you have the HMM lambda. You can similarly define a backward algorithm, all right? Just sort of starts from the back and goes backwards instead of the front. And it's a recursive algorithm that computes the likelihood of being at state time t and seeing the remainder of the observations. Again, given the HMM. So, that's a joke. Did you get that joke, Megan? You got the joke. She's quiet today, which is an unusual thing for Megan. Here's how it works. If we have the HMM, so if we know the HMM, we know A and B and pi, we can use the forward algorithm and the backward algorithm, and this is part I'm not going to show you, to estimate, that's what's cap E, the distribution of what state I'm likely to be in at time t, okay? Because one has to do with the sequences forward, one has to do with the sequences backward. I can evaluate the probability of the whole sequence. That allows me to estimate what's typically called gamma I of t, the probability that I'm in state 1 at time t, state 2, state 3, all right? I estimate that distribution. Well, if you give me that distribution, and I've actually seen at every time t what was observed, then given the likelihood that I'm in each of the states, probability that I'm in each of the states, and the observed data, I can figure out what the most likely B sub j of k. That is, what do I think the emission probabilities are? And I picked the ones that would maximize the total observation probability. It's no different than saying maximum likelihood, if I'm drawing something and I pull, I pull 10 things out and 7 of them are black and 3 are red, I say there's a 70% chance of being black. That value is the one that would have maximized the likelihood of pulling out 7 of them. It's a maximization procedure. So I can choose the B sub k's that maximize the total observation, given those probability, the idea of which state I'm in, okay? Also, given that distribution, I can also say, well, if I think there's a 75% chance that I'm in state 1 at this time and a 90% chance that I'm in state 2 at the next time, that tells me that, well, the likelihood of going from 1 to 2 must be kind of high, right? And basically by looking over all of time and looking at my guess about the states, I can come up with the best possible transition probabilities. And when I say best, again, the ones that maximize the probability. That gives me my new AIJs, and I've got new BKs. I can also guess new pi's, but those never matter. That's my new machine, right? So after I do the M step, called the maximization step, of getting the new A's and B's, I now have a new machine. I can go back and do the E step again. I can estimate the probabilities of being at a particular state at time t, and I redo that process. And that iterative process, it's called expectation maximization. The particular algorithm for HMMs was called the Baum-Welch algorithm. Like I said, there's plenty of tutorials out there for you to look at it. The fundamental idea is that by using these recursive algorithms and then estimating the probability of being at a particular state at a particular time, I can re-estimate the machine. We'll talk about HMMs just in general, and then we'll move on to vision. In general, HMMs are generative models of time series with some notion of a hidden state. That is, they can talk about the probability of generating particular output. The forward-backward algorithms, those recursive ones, allow you for computing over the states, and you can also use that computing to train up your models. And I will say that HMMs were, their big win was in, originally in speech recognition, dealing with low-level auditory features and using that to recover phonemes and then phonemes into parts of words and things like that, and then in computer vision. Although I will say there's a whole new area these days called conditional random fields, which is really better, as I mentioned, if you've got a long sequence and you want to do segmentation, conditional random fields are a slightly more complicated version. Actually, they're a significantly more complicated graphical model of representing time series, and it tends to do better than HMMs for the actual segmentation. But from the notion of a generative model of saying, is it an A or a B or a C, HMMs are still used extensively. So I want to look at HMMs in the context of what's referred to as gesture recognition. It's sort of an old approach, an old problem, especially using HMMs, but it's a good paradigm. There's a conference called Face and Gesture in computer vision. So obviously gesture must be important because there's a whole conference called Face and Gesture. And it's a long story going back to colleagues of mine about why face and gesture were put together. I'll tell you to you some other time over drinks of some flavor. The typical scenario was you do some examples of each gesture. The system learns or is trained to have some sort of model for each, and like I said, lots of things used HMMs. And at runtime, one would compare the output of each of the different you would evaluate what you saw in terms of the likelihood of the sequence, and if that probability exceeded some threshold, you say, aha, a particular gesture happened. So this was done, as I said, a while ago, sort of the mid-90s. Then it started to taper off because partially this whole idea of having sort of individual trained gestures that people would do to make something happen, that didn't feel like just the recognition of individual vocabularies. So it sort of tapered off. But then all of a sudden, new life was injected into the field of gesture recognition, and it was because of human-robot interaction. Okay? People really love the idea of being able to gesture to a robot, which if you've ever been to my lab, we sometimes gesture to the robot in a not-so-friendly way. But this idea that you could do things and control a robot, first of all, speech is very difficult in a noisy environment unless you're wearing a microphone. Gesture, you might be able to do something more remotely. And it was just this general idea that was kind of cool to be able to make some gestures and have a robot respond appropriately. So and here I just pulled out a paper. In fact, it's 2014. This was at some conference that just happened, and since I'm recording this in 2014, it's I'm not making this up. This is what's currently going on. I'm not advocating one way or the other the importance or whatever of this particular piece of work. I actually pulled out an older piece of work focusing just on the gesture. This is by Nam and Wan, of recognizing hand gestures using some HMMs, just because it was very paradigmatic of how people would do things. What was kind of cool about their system was they had a bunch of different gestures that they wanted to indicate, like nouns, chairs, vase, lamp, ball, because of course that's a natural vocabulary. I have no idea. And then you want to do things like put it down or bring it or or discard or jump. I don't even know why that was a particular verb that they wanted to use. But the idea was that there was a fixed vocabulary. The inputs that they were going to use, and they were going to control it with the hand, was a couple of different kinds, right? They had something to do about hand configuration or posture, something to do with how your fingers were shaped, okay? They also had how you were holding your palm, and then they had a sequence of hand position, a motion, okay? And they wanted to use all of this information to make a decision about what gesture you were indicating. So the first thing you should ask is, how are they getting this information?
How are they getting this information?
Boy, Megan woke up. Well, they were using something called a data glove. Here's a picture. So a data glove is this thing that you could wear on your hand that had both accelerometer and gyro information about how it was being globally manipulated, and also knew something about how you were moving your fingers. So they built this kind of interesting system, and the reason I liked it is they actually are using these three sensors, the angles, the orientation, the position, right? And what's interesting is they use the HMMs just to get information about that motion trajectory, right? They had other methods of putting into their system how your orientation was changing and what the angles were, right? So the idea is that you might have some basic overall probabilistic integration system, and in order to make use of that, you needed things that would output the probability or the likelihood of getting a particular movement for a given gesture. And HMMs were exactly the kind of thing to use for that. And in fact, discriminative methods might have been harder to use for that because they need to combine these probabilities. So here was something very simple that they did. They took I shouldn't say very simple. Here's what they did. It required some engineering. You take your raw data, which was a trajectory that you would move in X, Y, Z. And the first thing they did was they said, well, your gesture is pretty much planar, right? The plane could be this way, could be this way, but the idea is that a single gesture didn't move in more than a plane. I might even go like this, but you'll notice even this figure 8 is in this plane, right? So they find the plane that the gesture fit best to, project it down, and then they did what's called a chain code. We didn't actually talk about chain codes. If you did some machine vision, you would learn about chain codes. It was a way of encoding a contour as being, maybe you could only take one of 8 steps, right? So you go up, you take a direction, north, you go northeast, you go east, 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 south, southeast, southwest, and then eventually you come around. And you could think of the entire contour as a sequence of discrete steps, right? So north, east, south, right? So sequence of discrete symbols, aha, HMMs. So they trained a very simple left to right HMM. Left to right meaning that you go through every state and you don't skip states. You have these loop back things because you might stay in a state for a while where essentially you're going let's suppose you were going north, northeast, but you didn't have that as a direction. Well, north, northeast, that state, you might sometimes put out north, sometimes put out northeast, et cetera, whatever, but you'd stay in that state for a while. It would output, there'd be 2 symbols that it could output with high probability, but that state, for example, would never output south. Okay, so that would be you'd stay in a state for a while. So they trained up these HMMs, and they did 1 HMM for sort of each gesture. Okay. They also did some stuff that had to do with what they call junctures, doing transitions between gestures so that it could parse them. I don't think I'll talk about that here. I just will say that people hook up multiple HMMs together to form sort of an HMM that can deal with a sequence of gestures, and it's not too much more complicated than the original HMM. So they do that, and then they test it. And because they're testing it on a very controlled vocabulary, using features defined to work, and because they want their paper to be accepted, okay, you see results that look like this. Okay, so here there are hits. This is the percentage of hits are the percentage of the actual targets that were correctly labeled. Misses are when you don't label a thing correctly. And as you can see, they're doing tests of over 100 of each of these examples, and almost all of their gestures are recognized with a relatively high accuracy. You can see there were 1 or 2 that were not so high. And showing a table like this is one thing. A slightly more interesting table might be a confusion matrix. This is like we showed for the SVMs for the bag of words, where if you go back and take a look at the slides, you'll see a table that says how often is an airplane confused as a face, or that kind of thing. Normally, if you're going to report results about doing classification, don't just provide hits and misses, also provide a confusion matrix, because sometimes the actual source of the performance is that some of the categories were much more confusable than the others. You have no way of knowing that if you just report performance rate overall, but you need to be able to see the confusion, which element or which categories were confused with which categories. That's all we're going to talk about in terms of HMMs and gesture. I'll say the good things about it were it was a learning paradigm, right? So you define some features. By the way, you have to define the right features. You collect some well-annotated data, which also takes some work. But given that, you're able to train your HMMs by just giving it the data. So it's a learning paradigm, and that's good. The training is a little bit slow. It's not very slow, but recognition can be very fast because of that recursive, those recursive algorithms we talked about. Running those is very quick. So that works really well. Of course, not everything is perfect. They're not as good for segmentation labeling as some newer methods. I mentioned conditional random fields earlier. If you actually have something where your training data has particular underlying states and you know what those states are, so it's not even really a hidden Markov model. It is a Markov model, but your training data, you know the underlying states. and you're seeing an observation and you want that state sequence for that segmentation, there are now better methods, and I mentioned conditioned random fields. In general, this stuff requires a reasonable amount of data to train. One of the reasons it was used for speech is we had lots and lots of data. Although I will say that HMMs may require less data than some of these more discriminatory